Hi, welcome back to the lecture on a practical guide to quantitative finance interviews. So I'm Alan. Today is going to be the final chapter, final lecture on brain teaser. And mainly we are going to talk about the pigeonhole principle. It's actually a quite useful principle in the interview, which can help you to simplify a lot of questions using this rule. And let's go for it. So first, let's discuss a little bit about this principle itself. The basic version is that, and basically it's why it is named after as a pigeon. So if I have fewer pigeonholes than the number of pigeons, and I put every pigeon in a pigeonhole, then at least one pigeonhole has more than one pigeon. It seems a little bit stupid and too obvious, but let's write it down. So holes, this is the first thing, and pigeons, and at least repetition. So it is telling you that if we have n holes and at least m plus 1 pigeons, then at least m plus 1 pigeons have to share one of the holes. I mean, it sounds a little bit abstract. What does it mean? So now I'm trying to convert them into statistical language. This hole is actually our sample space. As, for example, if we use color as an example, there could be red, green, or something like that. And this pigeon is our observations or sampling. For example, how many colors can we find from n hats? Then this number n hats n is gonna to be the pigeon in our principle. And at least it's going to say, for example, if we have 100 hats, well, they can only be red, yellow, or green, these three colors, then at least, then we can see that mn plus 1 equals to 100, while n equals to 3, then m is going to be what? 33. So at least 34 hats have same color. So, I mean, if you do not know this principle, you can still solve this kind of problem, but it's hard to explain your logic to your interviewers. But if you know that, you can just say, I apply the pigeonhole principle and I get that. And it's going to be super fast. Let's see some questions. The first question is matching stocks. So basically, it contains 2 red socks, 20 yellow socks, and 31 blue socks. Being a busy and absent-minded MIT student, well, I hope I am an MIT student, but I'm not. I'm from Columbia, but yeah. You just randomly grab a number of socks out of the drawer and try to find a matching pair. Assume each sock has equal probability of being selected. What is the minimum number of socks that I need to grab in order to guarantee a pair of socks of the same color? So how many colors we have? We have red, yellow, and blue. So again, we have the whole, and it is 3, right? And we have the number, and this is going to be our n. We have the pigeon. In this case, is what? Is the total number of socks. So we want a pair of socks of the same color. So which means the at least part, we just want two, right? At least two is going to be the same color. So we know n and we know m plus 1. And now we are going to solve what? Mn plus 1, right? So we can derive here m equals to 1 and n equals to 3. So this is going to be 4. And we solve that. So basically, what I'm going to tell you is this quite simple question is that as long as I know 2 out of the 3, if I know whole and at least part, I know the number of pigeon. If I got the pigeon, I got the at least part, I know the whole. So I just need the 2 things to refer to this third one. And now let's go to the second question. I believe you already have some sense about applying the Pigeon principle. So let's first read the question. You are invited to a welcome party with 25 fellow team members. So each of the fellow members shakes hands with you to welcome you. Since the number of people in the room haven't met each other, there is a lot of random handshakings among the others as well. So you don't know, maybe like there are other 2 friends that keep handshaking with each other. I don't know. And so because we don't know the total number of handshakes, can you say with certainty that there are at least 2 people present who shook hands with exactly the same number of people? So again, whole, pigeon, at least. So I think the key part to solve this kind of question is now become how to frame them into this pigeonhole framework. We already have the at least here. We only need 2, right? So this is m plus 1 and m equal to 1. And he's asking us, can we say? So what's our sample space in this case? Well, that's the most important part for this question. We define the edge as the number of, we define the edge as the number of handshake. Time. What does it mean? So this sample space originally can vary from 0, 1, all the way to 1, all the way to 25. So in total, there are 26. But now, due to what? Due to each of the fellow has already shakes hands with you to welcome you. So 0 is gone. And there are only 125 left. And we know that n equals to 25. And how about mn plus 1? Mn plus 1 equals to 26. And we already got 25 equals to 25 plus 1 people. So can we say with certainty? Yes, we can. We can say with certainty there are at least 2 people present because it meets all the requirements and it satisfies all the requirements for a Pigeonhole principle to stand. And now the third question. I really like the title of this question. Have we met before? So I tend to, use this kind of way to say this sentence because I don't know if there is any How I Met Your Mother fan. It's a super classic comedy, just like Friends. And Uncle Barney in that series often says things like, have you met Ted? To trying to connect Ted with some girls in the bar. Yeah, it's interesting. So let's see the question. So we need to show me again that if there are 6 people at a party, then either at least 3 people met with each other before the party, or at least 3 people were strangers before the party. Well, if you are trying to solve it from scratch, it's going to be hard, but it's also quite intuitive. If you do the guess, you can also say that this is correct, right? But it's easy to explain that under the pigeonhole again. So we have the whole, we have the PG, we have the at least. So we know that it is asking us to, so the number n equals to 6, right? Oh, sorry. So this part, the mn plus 1 equals to 6. And what's our sample space? Our sample space equals to known each other and stranger. So equals to 2. And we know n equals to 2. So combining these two, we can have equals to what? M equals to 2 over 5, right? So at least m plus 1 will equals to what? To 7 over 2, which equal to 3.5. So at least 3 people meet each other before the party, or at least 3 people were strangers before the party. We solved that. And now let's count to our today's big boss, the counterference coins 2. So for counterference coins 1, we already solved that in the previous lecture during the thinking out of the box session. But this time, it's getting harder. So, and it's kind of different. There are 5 bags with 100 coins in each bag. A coin can weigh 9 grams, 10 grams, or 11 grams. So each bag contains coins of equal weights, but we do not know what kind of coin a bag contains. You have a digital scale, the kind that tells the exact weight. So how many times do you need to use the scale to determine which type of coin each bag contains? Well, so to solve a complex question like that, again, using our common techniques, we have like 9 grams, 10 grams, and 11 grams. They are not good numbers. So first we want to simplify them into -1, 0, and 1, right? Then how many times do I need to use the scale? You see every bag has like 100 coins. So it's not an easy task to solve it directly. What we can do is that we start from 1 bag. Let's assume there are only 1 bag. And then we just need to take 1 out, right? We just need to take 1 coin out. If it's 9 grams, then it's going to be 9 grams because all coins are equal weighted. How about 2 bags? For 2 bags, there are actually more combinations. So it can be like, if we use this notion here, so the first one can be -1, and the second one can be like, so 0, -1, 0, 1, right? And then we can also have -1, 0, 1 for them to be combined. And the sum is going to be -2 here, -1, 0, -1, 0, and 0 here, 2, 1, 1. So you can see the range is -2 to 2. And there are in total what, 5 possibilities. But the combination is what? Is we can be either -1 or 0 or 1 for every bag. So the combination is 3 multiplied by 3 equals 9. So which means what? Because we only have 5 possibilities. And it is going to be 9. It's smaller than 9. So we cannot find our result by just taking 1 coin from each bag. So how many do we need to take? The thing is that we need to take 3 coins from the second bag. Why it is the case? So for bag 1, we take 1 coin. And for bag 2, we take 3 coins. Then the total combination is still 9. It's still 9. Why it is the case? Because all these 3 combinations are the same. They either all -1 or all 0 or all 1, right? But again, this time, these possibilities is going to change from what? It's going to change from -4 to 4, which gives us 9 possibilities. Now we use the pigeonhole framework. We got the hole, which is 9 equals to n. We got the pigeon, and so it is going to be, oh, sorry. So this is 9, and at least the pigeon is going to be nm plus 1, right? And we got at least 2 going to be the same, and it's going to be, so this should be 10. But this is for at least 2 to be in the same. But we only need 9 to allocate 1 for each, right? So we can put like -4 to 1's possibility and 1-on-1 matching. So now we can consider this case that for 3 bags. So how about 3 bags? For 3 bags, of course, we take 1 from bag 1, 3 from bag 2, and how about bag 3? We know the total combination is 3 to the power of 3 equals to 27 this time, right? So we need to be larger than 27. So how can we do that? Again, the thing is that we wanted it to be 14. Oh, sorry, 13. So we want to take 9 from the second bag, which is 3 to the power of 2. And maybe you can see the pattern right now. So which means for 5 bags, because if we take the 13 out, it's going to be -13 to 13, the total possibilities of all the coins taking out their sum is going to be varying in this range, which gives us 27 possibilities, right? So for 5 bags, we just need to take 1 from 1. Bag 2, we take 3. Bag 3, we take 3 to the power of 2 equals to 9. Bag 4, we take out what? 3 to our 3, 27. And bag 5, we take 81. And it's going to solve our question. And in that case, we can determine the coin type of each bag in just 1 weighting. And so it's going to be the end of today's lecture. Hope you enjoy it, and I hope you know more about this pigeonhole principle. We are going to see you next time. Next time, we are going to start talking about calculus and linear algebra. Yeah, see you.